Hello and welcome to a webinar to the introduction of Bluetooth direction finding. Let me start this off with some practicalities. The webinar duration will be about 60 minutes. Questions are highly encouraged. You can type your questions in the question bar at the top right corner of your screen. These questions are also what we're going to look at the end of the webinar for the Q&A. You can use the chat for chatting, but we will not use the questions in the chat for the Q&A at the end. If you want us to use your questions in the Q&A at the end, please use the question function. A recording of this webinar will also be available with the presentation afterwards on webinars.nordicsemi.com. I am Finn Boetius, I am today's host. And with me I have Paul Kastner, Technical Marketing Manager and the person in charge when it comes to angle of arrival and angle of departure. So everything that is related to Bluetooth direction finding. As a side note, just because we're not considering questions in the chat for the Q&A at the end, it's always nice to see an active chat. So please feel free to use the chat and say hello to one another and maybe discuss the webinar. And with that, I think we can get right into it. Paul, you want to go?
So over to the agenda for today. What we're going to talk about is, of course, Bluetooth AoA and AoD. So I will do a short introduction to the topic. We'll discuss a little bit about the differences between AoA and AoD. We'll talk a little bit about the physics, IQ samples, scope for what is part of the Bluetooth specification and where the specification actually ends. Talked about connected versus connectionless. And part of the connectionless part here, we will also talk a little bit about periodic advertising. I will talk about the samples that are included in the SDK, supported hardware tools, as well as devices, and partner support in the end, before we move over to the Q&A part. So this is part of what we're doing now. This is as an introduction to the direction finding. This was the hallmark feature of the Bluetooth 5.1 core specification that came out a few years ago. It does require some additional hardware to the radio to be able to support this one. I will talk more about that one in a later slide. This is an optional feature, which is very typical for what happens when Bluetooth adds functionality. They add features, but most of the new features where you get new functionality and so on comes in as optional. There are very few mandatory features. These are usually for the erratas to fix up problems they have seen before, weaknesses and so on. But most of the new hallmark features are optional. So this is how we can have a 5.3 certified solution without actually having support for the direction finding part. Now we do have it. And the direction finding is there to enable positioning solutions, and it does that based on direction of a signal using phase detection. And this is actually the first Bluetooth standard where we would say that this one supports real-life positioning solutions, where you can actually use it to do positioning. Earlier we had the proximity solution, but the proximity solution doesn't really give you the opportunity to do proper positioning because the range where it's usable is very, very short. And because of that, you can't actually build up well-functioning systems that use this one. And the target for this one is, of course, as with everything with Bluetooth, to be able to do cost-efficient, ultra-low power devices. And in this case here, the tags are able to be that. So there are a lot of use cases for doing direction finding. Some of the primary ones and the ones that we see the most often asked for is for asset tracking, where you want to have a real-time locationing system, RTLS. This is really well suited for doing that. And the key drivers here is the ability to do low cost devices to be able to track them. And when you do asset tracking, you normally want to track them inside an area, which means that you have a control space where you want to be able to locate things, and again suited for direction finding with Bluetooth. You can also use it for doing wayfinding, and then you have the proximity solutions where you have point of interest, where you maybe want to be able to discern between multiple users that are close to it to see which one is in which position. Like in this case here, in front of a display, you will be able to see that yes, they're close to the display, but you can also see which one are on what side if one of them has a phone, for instance, and to do item finding. One of the reasons why we're doing this webinar right now is because even though we have had a Bluetooth, we have a solution for direction finding in the SDK for quite some time, this has been experimental, which means that yes, it did work, but we didn't have the Bluetooth qualification, so it wasn't possible to build a compliant product and get it certified. This changed when we got to the Connect SDK version 2.1.0, which we released in, or which we tagged in September. At that point in time, we did get a qualification for the host side that's included in the SDK. We also had a qualification for the soft device controller for AoA transmitter, and that one came in already in the tag 2.0, which was done in June 2022. But a key part that came in now with the 2.1.0 tag was also that we did certify the Cepheid controller subsystem, so basically the Bluetooth link layer, for all features when it comes to both transmitter as well as receiver, for AoA as well as for AoD, and so all of that came in now. And because of this, since we have had the system out there for a while, we have been getting feedback from customers who have been looking at the solution we have and asking questions about how to do things, how things work, and so on. So there are some of the slides here are basically answering frequently asked questions. So for if you are unsure and if you don't exactly know how all of these things work, I will cover it now in the later slides when we go through this one. So when you're looking at the difference between angle of arrival and angle of departure, these are based on similar approaches where you have one unit which is movable and one unit which is static. The static unit is a larger device where you have a multiple antennas to make an antenna array, and the movable unit is a simpler unit with when it comes to the hardware where you have a single antenna. When you're looking at angle of arrival, which is the one that we typically see being used for asset tracking, the transmitter on this side here is a very simple beacon. It only requires to have a single antenna. It doesn't need to do any kind of advanced calculations. You don't need a lot of processing power. You don't need a lot of memory. And because of this, it's possible to do the transmitter here as a low cost, low power consumption device. So you'll be able to make a tag that can run from battery for a very, very long time with an angle of arrival transmitter. On the receiver side, it becomes quite a lot more complex because on the receiver side, in this case here, you need to have one antenna array. And this means that you need to have multiple antennas on the unit. You need to have a lot of RF switches on this. And this is being used then for processing and finding the angle of the incoming signal. A little bit more about that one in the next section. But since you need to be able to get all of this antenna data, this is being read out from the radio as IQ data. These are needed for the angle estimation. There's quite a lot of IQ data coming in, so you will need to have enough RAM on the device to be able to buffer this up. And if you want to do the processing of the angle to find what the angle actually is, you also need to have a processing power on the device to be able to do that. The second option is, of course, that you can offload the data to another device in the system to push the processing to a more capable platform, to the cloud, to a gateway, and so on. But again, then you need the bandwidth to be able to get the data out of the device quite quickly. So this is a higher cost device, and it's higher cost because, yes, you need the larger PCBs because you need the multiple antennas and you need more of the components to do the RF part. But it's also a higher power consumption device because normally this one will be reading data or looking for transmitters all the time, so you'll keep the radio on most of the time. So we don't see these ones being used as battery operated devices that much. When you do angle of departure, as you can see on the figure here, it looks a lot the same as on the previous slide. The difference now is that the transmitter is the one with all the antennas on it. So this is now still a beacon. It's an advanced beacon. The code that runs on it is not that much more complex than it is on the transmitter side, on the AoA side. The only thing that it needs to be able to do now is to control the RF switches directly, which is done by hardware inside the part. The more advanced part here comes that you now need to have the antenna array. So you need to have the larger antenna with it. But you still avoid having to do any IQ calculations and so on. So because of this, it's a medium cost device because the PCB size goes up with the antennas and so on. But the power consumption can still be kept low because it's still only doing a transmitting. There's not anything more being done on this side compared to what you do with a standard beacon. On the receiver side, you now have a single antenna, which makes it a movable device, which means you can transfer it around. You will still need to be able to download all of the IQ data, and you need to have the processing power to do the calculation of the angles and the connection to offload the data. And this one also means that you need to have access to the antenna design data, so the antenna design of the transmitter side, because you need to know the distance between the antennas, you need to know the sequence of the data coming out of this and so on. So this is a much higher cost device and a higher power consumption device. This is typically where we see these ones going into. The target market for this would be to use it for indoor locationing or indoor map services for using a cell phone, where you have all the processing power and all the feed and the internet connectivity to get all the data in and out of it. What you would be lacking on, and since you only have a single antenna, you can make it small enough to be portable, so you can fit it inside the phone. The antenna arrays are way too large to fit inside the phone. We still haven't seen any phones pick up AoD as a functionality, but this is what it is designed for. So we'll talk a little bit about the physics and how everything is set up when it comes to the Bluetooth specification. So when you're looking at this one, the way you are doing the angle resolution is that you basically have a standard Bluetooth package with the preamble, the access address, and so on. But what is new and that came in with the Bluetooth 5.1 is this constant tone extension that comes in the end. This one is the feature that allows you to do the phase shift measurements. And to be able to do the constant tone, you need to do a continuous carrier of a 1 coming out of the radio, and it needs to be unwhitened because standard Bluetooth low energy packets are all whitened, so that you don't have a constant tone with that one. This one requires a different hardware, and this is why there are a lot of devices out there that are Bluetooth 5, Bluetooth 5.1, 5.2, and 5.3, and so on, that do not support direction finding because they don't support the constant tone extension, which is an optional feature. And the packet size or the packet format looks the same both for connectionless and connected or connection-oriented modes. You do put the CT at the end of the packet. Do have in mind that this is only supported for 1 megabit and 2 megabit PHYs. You cannot use direction finding with coded PHY, and the reasoning behind that is that as soon as you start doing the constant carrier, then the constant tone, you would negate all of the benefits with coded PHY, so you wouldn't get any range increase. There are a lot of different options when you set this one up. You can have a programmability on the length of the CTE. You can set up if you're going to use the 1 megabit or the 2 megabit PHY. You can have how many antennas you want to have. Everything between 2 antennas and up to 38 or to 75, depending on the time slot you're using. What is common for this one, there's always a guard period in the front, and there's always a reference period. And in the reference period, you will always take 8 samples. And the reason behind that one is that the reference period samples are being used to establish the baseline on the frequency being received on the radio, and to get a time base and a phase, correct phase that you will be comparing with, and then you will switch to all of the other antennas afterwards. And receive the signal for each and every one of them, maybe multiple times, to then be able to check what phase changes has been between the different antennas. So when you're doing these measurements of the phase, what you typically do then is you start out with having an antenna with multiple, an antenna array with multiple antennas on it. So in all of the following documentation, I will be talking about a specific antenna that we have designed inside Nordic that we use for all of these kind of measurements. So this is a 12 antenna. It has 12 patch antennas on it, so that, it all combined with high performance RF switches, so we can select which one of the antennas is connected directly to the radio. Only one will be connected at any point in time. And the hardware will scan through antennas in a predefined patterns. This is programmable which way you want to do it, depending on what algorithms you're running and so on. Some of them will have benefits above others. And this is an array design. So as you can see here, basically it's a 4x4 matrix, which should have been 16 antennas, but we have taken out the 4 in the middle to fit in all of the electronics to it. So we have a matrix like this. This one will give you 2 angles. While if you want to do a line antenna where you have only one line, for instance, you have the antennas from 11, 12, 1 and 2, you will then only get a single angle out. And have in mind that with direction finding, you will only get angles. You will never get centimeters and so on. You will get an angle from the incoming signal in AoA or from the outgoing signal in AoD. And then you can use these angles then to do triangulation to find out where points are in space if you have multiple antennas. So the defined files for this design is available, and you can use it to build your own. As you can see here, this one is 20 by 20 centimeters, so it's a fairly large FR4 PCB. So it's not a design optimized for cost, it is optimized for performance to make sure that we have a reliable starting point when we're doing all the measurements on our side. You can also buy this one from Inside SIP as an ISP 1907 AoA DK. One important item with this one is the distance between the antennas. As you can see here now, with this system, we are running with an antenna distance of lambda 0.4. It's 5 centimeters between the centers of the antennas. This is shorter than half wavelength because it reduces the complexity on the algorithms that you run to find out the direction of the incoming signal. When you have an antenna like the array antenna we have here, there is a coverage area where you can actually use it reliably. So this will be, in this kind of design, it will be a hemisphere above the plane is covered. If you get very close to the plane, you will see a degradation in the performance. For this design, we see it when you start to get closer than 15 degrees to the design. And this has to do with the antennas being chosen, being patch antennas. So they have a very good performance for projecting the field out of the directly out of the plane, but they don't work well in the plane. If you want to do a line type antenna where you only want to have one angle out, you do different antenna design, and then you get a much better performance in the plane of the PCB. But then again, you only get a single angle coming out of it. So when you're looking at the data coming into the radio, as I said in the beginning, the first 8 microseconds is the reference period here. I'm trying to do some graphs here to try to explain how this will look. And this is one of the areas where we have seen a lot of questions coming in, where customers who are not used to this or haven't looked at it don't necessarily grasp how to visualize the data, and why visualization in some cases just will make you more confused. So the blue series one here is the reference antenna. The signal that we're running with right now is positioned directly above the reference antenna, very close to it. It's only 1 centimeter above it. And the reason why I use this 1 centimeter is because then you get a very large phase change in the signal, because the angles become very, very pointed. So when we do this one, you can see there's a nice sign in the beginning for the blue one. There's only 1 point every microsecond, so because of this, it doesn't look perfectly covered. If you had oversampled, it would show up as much more clearer as a sine wave here. In this case here, I simulated with theoretical values, and this is just to showcase how things would look like in an ideal world. And with this one, then you can see that when we start sampling later on, when we start sampling the different antennas, we sample with a timescale which is 2 microsecond or 4 microsecond. And because of this, it goes up with 500 kilohertz. So because of that, you will get the same amplitude on the input signal absolutely for every sample. So it will look like a flat line. It's definitely not a flat line, but it's like an artifact of what happens when you start doing undersampling. What would happen in real life is, of course, that there will be a mismatch in the frequencies. You never get perfect matching like this. Again, the reason why we do the reference here. And what you can see now, it looks like the signals in the sampling period after 16 microsecond, it looks like they are moving slowly. Of course, these are still sine waves running with the same frequency as the blue line. It's just that because of undersampling, they look to be not moving that much. So again, one of the reasons why we say that this is a little bit tricky when it comes to how you do the visualization of the data. So in a lot of cases, trying to do a visualization of these data will just make it worse. Same if you start looking at a longer period, it will look like there are sine waves again, but with a lower frequency than the blue one, and the frequency of these ones will actually be the mismatch between the transmitter frequency, the carrier frequency, and the receiver carrier frequency, as well as the modulation index, because this one is modulated as analog voltage, or as an analog based frequency. So it's not a PLL of a crystal or anything. So it will be about 500 kilohertz. It's not going to be exactly 500 kilohertz. It will be very stable, which is necessary to be able to use it for the direction failing, but it will vary a bit. So again, if you try to, when you pick out the data from the antennas that you're actually looking at, because as I said, what you do is you measure the phase for each and every antenna, and then you pick one at every sampling interval, which is 2 microsecond or 4 microsecond. And if you try to visualize these, you will see again, you get a very strange shape. What you should do instead is to look at the phase change of the different antennas compared to the reference antenna. So this is why what you do is you take the first 8 sample, which is the reference period, you use these ones to find the frequency of the measured signal, which should be around 250 kilohertz or around 500 kilohertz, depending on the 1 megabit or the 2 megabit setting. But they will never be 250 or 500. They will be around that. You use these ones, then you establish what the phase is at any given point in time, and then you just calculate what the reference phase will be for each and every one of the sample intervals later on. And then you calculate the difference in the phase on the input signal compared to the reference signal. And this is the data that goes into the algorithm to try to find the direction of the incoming or the outgoing signal, depending on AoA or AoD. So there's a lot of advanced math involved in using this one. There's a lot of material out there on the web on how to build up these algorithms. There are different strengths and weaknesses with them. Have in mind that this is something that's not new to Bluetooth Low Energy. It's been used for a long time in a lot of radar systems as well. So to give you a little bit of insight into what you can see and what will be limiting the range of the system is that if you're looking again at this, as I showed earlier, this is the phase shift that you will be detecting in the radio at a 1 centimeter distance. If you increase the distance to 100 centimeters because of the angles now being changed, so there will be the transmitter is a lot, how to say, further away, so the angle difference and between all of the antennas and the transmitter will be much lower. And since they become smaller, the phase difference between the signals will also be smaller because the difference in length compared to the total length shrinks. And if you go further on, so this is for 1 meter, if you go further on to 10 meters, you will see now that now the phase drift between them is becoming also a lot smaller. And because of this, you get to a certain point where the phase shift between all of the signals becomes so low that you basically won't be able to distinguish any angles. We have done testing internally on our side up to 20 meters where you can get a reasonable functionality. Going further away than that will impact your performance. We have customers who have done testing for several hundred meters, but they use different algorithms. They use the same antenna array as I've used and shown here, but they got significant longer range. But again, they use completely different algorithms for this, and they also had very little reflection because they were looking at things in open air, so they were not targeting things close to the ground. There were no walls or anything around them. So another frequent question that comes up is IQ samples. What are they and how to use them? So the thing is, when you're transmitting things over the radio, we are transmitting basically one signal, which is this green line, as you can see at the I plus Q. So that's the sine wave that goes over the air. When you want to do the demodulation of the signal and you're going to go sampling at specific points in time, if you try to sample the green one, you will get very bad results because the amplitude can change. If you're getting the samples close to zero, it will be very difficult to see that. So normally what you do in the radio, you do demodulation with 2 carriers that are 90 degrees phase shifted, and then you get the I and the Q data. And when you have both of them, it is much easier and much safer to be able to convert from those I and the Q data and to reconstruct the signal and to get the phase data out directly. So it's a much more robust way, and this is how everybody does it in digital radio. And because of this is the way or the data format that comes out of the radio when you're doing direction finding. So there are some very easy ways to convert it. Basically, to get the phase out, you take the arctan of Q over I, and you can find the amplitude by going through this simple algorithm. So it's very important that when you're looking at the data again, that you never try to visualize the I and the Q data. This is a lot of customers who have tried to do that, and the way to do that is always to take the data and the I and the Q data and calculate out the phase and the amplitude. Those are the data that goes into the algorithms to find out the actual direction. One thing to have in mind is that the Bluetooth spec states that the I and Q data should be 8-bit. And to be able to do that, the radio that we have samples with higher resolution than that. So we have to truncate to get the range down to stay inside the 8-bit range all the time. And because of that, we see that on the NR52 device and the 53 devices, the typical IQ values are seen in the 30 to 50 range. So the reason behind that is when you are receiving, we freeze the gain in the automatic gain control when we do the reference period in the beginning of the signal. So we freeze the gain on that part. And to ensure that we don't go into saturation on any of the other antennas, which can be higher, we have to keep the input signal down a bit. So because of this, you will typically see this one. It is possible to make more advanced algorithms for checking to improve the range there, but we haven't implemented it in our code. We are planning to add support for higher resolution, but that will be a custom solution, so it won't work with all commercially available code, but it will give you the option to get this. But if you want to change it, you can just go into the code for the controller side and change the way we do the truncation there. We're doing a simple shift operation to remove a few bits to make it work. One very important item is that saturated signals should return a -128. And the reasoning behind that one is to make sure that the code on the application layer can see that some of the signals that came from the radio were saturated, because then you can ignore the data, or you can say that this phase data shouldn't go into the algorithms. So when it comes to the specification, the Bluetooth specification covers all of the things that are on the physical side there. So it does cover the host functionality. It covers the ACI commands to use together with the direction finding or with the CTE and setting up the radio and all these kind of things. It does, of course, set up the on-air packet format, how the sample timing should work, both for AoA and AoD and so on, and it fixes in the IQ data format. And it also links in what packets can have the CTE appended to it. So there are some limitations on what you are allowed to do here. So as always with the standard, there is a focus on making sure that it's interoperable, that it will work on all devices, and that it won't cause problem for other functions that are using the same kind of radio systems here. What is not covered by the Bluetooth specification is the antenna array design. They just state that you need to have multiple antennas and you can have 2 or more. It doesn't state how to do the algorithms for calculating the angles. It doesn't have included in exchange of the antenna array design and so on. And it doesn't include the locationing. So if you want to be able to pinpoint where things are in the 3D space or a 2D space, that is not covered into the spec. The spec actually ends with the IQ data being delivered from the controller subsystem to the application. So the only thing that the Bluetooth specification covers is up to there. And this is where we also put the line on our side. So we also, in all our samples, we end the functionality when the IQ data is delivered to the application side. One thing, as I said, there is limitations on where you can put the CTE. And this has to do with occupation of spectrum. So that you can only append the CTE to packets in the data channels. And that means that you cannot put the CTE on the data in the advertising channels. So to be able to do connectionless solutions, the way this is being done then is that you have to use this periodic advertising. And with the periodic advertising, you still have data going through the advertising channels, the primary advertising channels, the 3 normal ones that you use for all normal Bluetooth part. But what will happen with these one is they will point to a specific point in time where there is going to be a packet in a data channel that will then link into a train of packets that are in the data channels. And when you get to this train of packets, these have a fixed interval. So they don't have any of this variability as you see with standard advertising. They are more like you would see in a connected mode. They are also using frequency hopping in the same way as you do in connected mode. So what happens is that when you are a locator and you're looking for a beacon or a tag, you will be scanning for the data in the advertising channels. As soon as you have found these ones, you will sync up with the fixed interval advertising, and then you will stay in sync with these ones, and then you will receive all of these ones continuously. So basically, to be able to scan multiple devices, you will need to be able to sync up with multiple advertising trains like this. And we are able to do that today on the link layer we're using. It supports up to 64 devices, but to be staying in sync with up to 64 devices at any point in time. But have in mind that the more devices you are synced with, the longer time you normally will have to expect to be able to find a new device as advertising. And this will also be impacted by the interval on the advertising side. The shorter the interval, the fewer devices you will be able to track at one time. This is why we are seeing that for a lot of solutions where you want to track a lot of units, you run with variable advertising intervals. So you run with lower intervals when things are moving and longer intervals when things are static. So why there's very often a motion sensor in these tags, to determine if they are on the move or not. So basically, as I said earlier, what you get out of the solution when you're using AoA or AoD, you get an angle or you get 2 angles. And you never will get an X, Y, Z coordinate. And this is why if you want to have an XYZ coordinate, then you will need to have multiple antennas or anchor points that you use to then calculate the angles from each and every one of these ones, and then you use triangulation to try to find the unit to lock down the unit in space. So to be able to do this, once the system will then need to know that the angles between the multiple anchor points and the movable object, but it also needs to be able to know the location of all of the anchor points and so on. This is not part of the Bluetooth specification, but this is again how you pinpoint things in a 2D or a 3D space. And then, as I said, the typical use case we're seeing here is for asset tracking. And the key driver here is the fact that the tag is a very simple transmitter. It means that you have a lot of small low-cost unit that runs with low power operation, and then you have a few locators that are fixed in space and are then being used as anchor points to find out where the devices are. And the location engine is then normally lifted out of the locator, and you have a separate unit doing it. So either an edge device or a cloud solution for it. So when it comes to what's inside the Connect SDK, we have multiple samples in the SDK. We always recommend that you go for the ones that we link in the NRF folder. These are the ones that we develop for the maximum functionality and that we do testing on all the time. So there are samples for a connectionless locator and a connected locator as well. So there is either is a central or connectionless locator. There is also for a connectionless beacon and for a connected peripheral. And these ones can be configured for AoA and for AoD. And the difference between these ones is that if you configure a locator for AoA, it will execute the switching. If you configure a locator for AoD, it will not use the switches, and vice versa for the transmitter side. And as I said earlier, these ones end where the Bluetooth specification ends. So we have the sample, they will be scanning for devices, they will be finding the devices, they will be listing what they are. You get a UART or a CDC connection out of the device so that you can see which devices is seeing in the area. And as soon as he has done this, it ends there. You will be able to print out the IQ data if you want to do that. It's not included in the samples, but it is a fairly easy task to do that. And the reason why we've done this one is because we wanted to provide the functionality that is needed for everybody. And the reason why we are not providing everything else has to do with the complexity of it. So if you're looking at this one, this is a software architecture for a locator on the full solution. So you will have the radio peripheral that will give the IQ data into the Bluetooth LE controller, and that will push these data over HCI up to the LE host. And then you need to have the angle algorithm, which has to be customer developed or third-party developed. And then you will have a cloud backend or a PC tool or whatever, to look at the data. And the reasoning for this is the fact that when you run these ones, you will have the antenna array pushing the data. So this is for an AoA. You will have the antenna array with the connection to the controller with the host and everything, included the PHY, that will push the IQ samples up to the application layer or out to the offsite for calculations. The algorithms will have a lot of standard things that you will see everywhere. But the key part here is that the antenna array and the antenna array will need to have an antenna model, and this antenna model will change with the antenna layout, the size, the position of the antennas and everything, and it's a hard dependency in there. And that means that it's impossible to make a fixed code that will cover multiple antennas. When you build the antenna array, you have to build the model at the same time. And this is something that is more or less impossible to support for a company like us. So because of this, we say that, yes, we will provide all of the functionality below that, and then the array and the model is something that the customer will have to do because it will have to be custom for each and every delivery. So what we have of devices here is the that supports direction finding in hardware, so basically supports the CTE part. For the transmitter side, both for AoA and AoD, we can support it with the 52811, the 52820, the 52833, and the 5340. Have in mind, for the 52833, we have a fully qualified hardware and software solution with the QDID for the RFI as well. On the receiver side, we can only use the 52833 and the 5340. And the key reason for this has to do with resources on chip. There is a significant requirement of RAM to be able to run to store all of the IQ data and cache it before you either use it for the calculation or before you get it off chip. And because of this, you need to have the 833 with the 128K of RAM to be able to handle this. So, as I said earlier, we stop where the Bluetooth stack stops, and that means that we also, as I said, we have a antenna design that you can get if you contact DevZone, but we don't sell any antenna designs. One of our partners has built an antenna which is basically built with our antenna design. So this is the one I mentioned earlier. This is done by Insight SIP. You can see the ordering code on the previous slide. This is basically an antenna array with 12 patch antennas, and on the back side there is a 52833 module mounted directly on the antenna board. There's a USB interface to it, so you can stream data out of it, and it comes with some module boards, so you can use it as transmitters. We also have support from u-blox. So u-blox has a couple of different antenna arrays, which they use with direction finding. They are smaller. They have a 4-patch and a 5-patch antenna solution. This is a design they do in-house. It's again 52833 based, where they also have the angle algorithms and a u-blox multi-locator software solution available. So they have a complete solution, and they take care of everything above what we deliver. So they build the application layer with the algorithms. They do the antenna design and link it up together, and they build the location engine. And we're actually doing a webinar with u-blox next week, so on the 12th of December. And they will be covering all their offerings they have, basically everything that's built on top of their Connect SDK. And how they extend it to be able to offer the full functionality. With the antenna arrays, the resolution algorithms, they're also going to do a demo on how you can be able then to fix devices in 3D space, so you can see where they actually located in the room. And thank you all for watching. Now it should be time for Q&A. Okay, so I will try to go through the questions that got asked in the questions tab. There are quite a few of them. The first one was if the IQ samples are available on the connectionless samples in the SDK, and yes, they are. So all the samples are, all the IQ data is available, but they are not being printed out when you run it. So if you open up the sample and connect the terminal to it, you will see the data being the external load being seen and everything, but the data is not being printed, and this has to do with bandwidth. The data is available. If you go through the sample, you'll be able to see that all of the IQ data is stored in an array, which is accessible from the application side. Okay, next question. So what's the accuracy of the azimuth and the elevation? This one depends on the antenna array. So the size of the array, if the antenna is larger, is usually easy to get a good accuracy. What we have seen with the antenna array that we are using used in the presentation, we see around 5 to 10 degrees of accuracy. If we have also seen that there are other antennas that get lower than this, but again, it depends on the size. A very good comparison was one of our partners. They did an antenna which was really well performing, where a large antenna did 5 degrees and a smaller antenna did around 10 degrees. So it depends on the antenna and it depends on the algorithm. So with a smaller antenna, you can get good performance, but then you will need to have a better algorithm. So it always depends, but 5 to 10 degrees is achievable for fairly, reliable. You will be able to see, I think the best we have seen so far has been around 4 degrees. Then there's a question about what's the maximum number of AoA tags that the AoA can detect. And this is, again, as I said in the presentation, it depends on the host. So the host will be able to, the host we are using today, or in the located side, is able to synchronize with up to 64 units at the same time, which means that we can keep track of 64 units. But when you try to do that, it becomes a little bit tricky to be able to keep the sync and so on, because the timing, there is only one radio. So if they start overlapping in time, it becomes difficult to track them. What you can do on the application side is, of course, that when you have the location of a non-moving device, you can say that I know where it is and then stop tracking it for a while. That means that you can track another unit. So by doing some dynamic scaling like this on the application level, you will be able to track much more units than 64, but it will give you a lower report rate when you're trying to do that. So if you're looking for things in a warehouse, for instance, as long as they're not moving, you don't need to worry about them. You need to know that they haven't moved in a while, which means you don't have to sample them all the time. And then you track the moving devices instead. So for these kind of things, for asset tracking in warehouses and so on, you will be able to track a huge amount of units with the stack as it is built today. And then there's a question how to make the integration with UWB. For direction finding, we do not integrate with UWB, and this is basically because when you're running the locator, basically the locator will be looking for devices all the time, so it doesn't make too much sense to try to do direction finding and UWB. The Corvo guys, they use our devices for all of the demos they do. So we also have extension boards for our for our kits, like the Thingy 53, where you plug in a Corvo extension boards to do UWB. So UWB integrates nicely with Connect SDK. Corvo has done a solution which we hope to be able to demo at a trade show not too far into the future, where we will be able to showcase how this actually works. But it is possible to integrate it, the UWB solution with NF Connect SDK. Specifically, this is one of the reasons why we have the MPSL. This is to make sure that you have you can get exclusive access to the CPU and so on when you're running the UWB part, so it doesn't overlap with the Bluetooth and get the interference there. The next question. Then there is a question, is there a ready reference solution on AoD from Nordic? Yes, the samples that are in the SDK do support AoD. So if you build the samples for AoA, or you can build them for AoD, both of those options will be available. But again, the limitation is, as for all of the code here, we end at the point where we deliver the IQ samples up to the application. So all of the algorithms and what is needed for transferring the data on the design of the transmitter antenna in AoD to the unit to be able to do the angle calculation will have to be delivered from your side. It's not part of what we provide from our side. Then there's a question of the maximum distance between the AoA tag and the AoA antenna array receiver. And this is one of the questions where we always will have to say, answer, it depends. The further away you are, the more difficult it is to get the angle calculated correctly. And this is, as you saw in the slides, because the phase difference between the different antennas becomes so much lower when the distance goes up. And this is pure trigonometry. The further the distance is, the smaller the angular difference between caused by the distance between the antennas becomes. That said, we have done testing up to 20 meters. We have customers who have done up to 40 meters in a parking lot space, and saw that yes, they got decent performance up to 40 meters. But we have also a university project where they did several hundred meters with it. But they did it in an ideal situation where they had free space. So there was all line of sights, no reflections and anything. And they were able to get a fix up to a few hundred meters with this one. But again, it depends on the environment you're operating in, what kind of location you have on the antennas, and so on. So it's really difficult to say. What's the sampling frequency of the 52833? So as I said earlier here, now the Bluetooth specification says that during the reference period, you should sample with 1 microsecond interval, which means 1 megasamples. And then you sample once in every sampling period where you sample for a new antenna. So to be able to do this, the requirement is to be able to do 1 megasamples. On the radios that we have on the 52833 and the other 52 devices and the 53 devices, we actually are able to do 4 megasamples. So we have the opportunity or the possibility to do oversampling both in the reference period and also to do multiple samples in each of the antenna periods. But that would not be Bluetooth compliant. So it's not part of what we do in the code that we deliver from our side. But it's not a problem to activate, to enable it. And we are looking into getting custom HCI commands to do that, so that you will be able to get oversampling. It just makes it easier to do the algorithms if you have more samples in each of the periods. So the original code that we did on our side when we did all the testing, we ran with 4 megasamples. Yes, how is this compared to UWB? The direction finding with Bluetooth compared to UWB will be lower power consumption because we don't need to run the UWB radio. The UWB radio is okay for power consumption for the transmit. It uses quite a lot of power when you're doing the receive. So for power consumption on a tag, the power consumption is better with Bluetooth. The time for fix is shorter with UWB, and the angular accuracy you get out of the UWB is probably also a little bit better. So the key advantage with direction finding on Bluetooth is the power consumption and the cost, because you get a smaller, cheaper device with lower power consumption, while UWB, because of the ultra wide band, has an advantage when it comes to the measurement solution, because it makes it easier to get an angular resolution and to get it faster and more accurate. Okay, then there is a question of how small you can get the antenna array. This one depends again. A smaller array will be able to get you a direction, but it becomes much more complex to get a good angular accuracy on it. So a smaller antenna makes it more difficult to get angular accuracy. And as I said, the antenna we use is a 20 by 20. We had the customer who did a 16 centimeter in diameter. That gave them 5 degrees or 4 or 5 degrees accuracy. And then it went to a 12 centimeter in diameter, and then they went to 10 degrees. So you can make a smaller antenna, but you're sacrificing on the accuracy. And then you have to also remember that when you do that, and the one thing we do say quite clearly from our side is that we don't see this one as being something that you will be able to fit inside a cell phone, which is where everybody wants to go, because the phone is just too small. You don't get enough spacing between the antennas there. So, which is why we say that AoD is what you're looking at for phones, because then you need a single antenna on the phone side. We do also see that it can be an advantage for the tags to have 2 antennas where you'd use one or the other, because then you have the possibility to find out to use antenna diversity basically if one of them ends up in a bad position, you can use the other one and so on. But that's the same as we do for all other communication parts. Okay, next question. And then there's a question, how much lag time is there when following a moving object? So this is, again, it depends. So if you want to have a high report rate to be able to track it quickly, you can do that, but that also means that you reduce the number of units you can track because you occupy the radio more for the one unit that you are looking for. So it is a trade-off between number of units you can track and the speed of the tracking part, which is also why you see a lot of the time when you have a lot of units you want to track them, you put a motion sensor in them so that when they are not moving, they don't advertise that often, and when they are moving, they advertise more often. But to give you an example, this is not using Bluetooth, but Coupa, one of our third-party partners for location services, they are not using Bluetooth, they're using their own proprietary solution. They track hockey players and the hockey puck in ice hockey, and they're able to track it over the ice rink. So it is possible to do it quickly, but again, you are trading off between speed of movement versus number of units you can be able to track at the same time. Okay, next question. And then regarding the area configuration and the single antenna case, the single antenna should preferably be omnidirectional, and this is basically to get the best performance there. If there are specific antenna technology recommended, it depends. There are some advantages with patch antenna. They are cheaper to use because they are only required to have the PCB side. One of the reasons why we picked them is because they give a good performance. There are advantages with going with helix antennas because they are circular polarization, so they are not as impacted by flipping or the orientation of the transmitter side. But it depends on the area of coverage you're looking for, because the disadvantage with helix antennas is that they are more directional on the locator side and so on. If you're doing a 2D antenna, basically where you want to have one angle out of it, you have a lot more freedom on this one, and there is a lot more antenna options to use then. You can use standard track antennas and meandering antennas and so on to do that. So for this one, it depends on what the use case is and how you plan to mount the receivers and so on. Okay. And then there is a question to how to position the antenna for the locators when you're trying to do triangulation. Again, this is where it becomes a little bit complex and which is outside the scope of the Bluetooth specification. Typically what you need to do then is to make sure that you have coverage of the area where you want to do the location with minimum 2 antennas, preferably 3 or 4, or for where you want to pinpoint the device. This is one thing that we do believe that it's in the agenda for the u-blox webinar, where they will showcase how they do this, where they do a live demo of tracking a unit in 3D space with multiple antennas. So this is, again, you will need to do the mathematics and set up and see the coverage areas for the antennas and make sure that all the areas that you want to be able to track units in are completely covered by the antenna radiation patterns. Then there's a question, since the raw IQ data provided to a user supplied the distance could be estimated if the antenna area is relatively large. Theoretically, yes. I have not seen it done. I think it will become, it will complicate the algorithm quite a lot. Okay, next one. And then there's a question if we have a list of third company helping with the angle resolution algorithms. Today, as I said, we will have a webinar tomorrow with uBlocks, which is one of the partners who do this. We were hoping to have another one next week as well with a second third-party company. But they were a little bit delayed, so we do plan to have a new webinar sometime in Q1 with another third party. So we will disclose more about this one through Q1. There will be some press releases coming out when their solution is ready to go to market. Next one. Then there is a question about standard algorithms. As I said in the presentation, we do not have any algorithms in the SDK today, and it is no way to make a standard algorithms. Algorithms will always be tied with the antenna. So because of this, we do not have algorithms in the SDK, and there is no plan to do that short term. Next one. So then there's a question about the Bluetooth spec covered IQ data as an output. If you already had the IQ data and so on, why can't we generate the angle and amplitude by the Nordic hardware itself? And this is because the antenna array will impact on how you calculate this. And so there is a hard connection between the antenna array and the algorithms that need to be run to find the angle. And because of that, it is impossible to build a hardware solution that will calculate the angle out of the IQ data without knowing exactly how the antenna array is set up. And that's the reason why this is a full custom implementation for each and every antenna design, and which is why we don't have a solution for it in the SDK, nor in hardware inside the device. Next slide. Yeah, so when 3 receivers are spaced 50 meters apart, you can use one receiver to compute the location. The limiting factor here is how many calculations you can actually do in a second. Then, so it depends on how fast you need to do the computation to be able to triangulate where the unit is. So it is possible to do the calculation for the angle resolution inside the device. It is also possible to use one of the microcontrollers to do to collect data angles from multiple units and then do the calculation for where things is in 3D space. The question is just how many units do you want to track and how fast do you want the report rate to be? Because it's all about how much processing power you have available to do that. So everything is possible. It's just software. It may not give you the performance that you require for it. Then is the concept if you can use AoA AoD in challenging environments. Yes, you can use AoA AoD, but have in mind that it will be impacted by multipath issues and so on. It works best in line of sight. So how the performance will be if you have a lot of rock and so on in between the antenna and the transmitter side, it will impact the performance level. How much is difficult for me to say. When multiple receivers are used in AoA computation, can one receiver be fixed? Normally what we do there is when you use multiple receivers, all units are fixed. As soon as you start trying to move a unit around, then you need to know where that unit is to be able to find the location in 3D space. So it complicates the mathematics to be able to do it. It's not impossible, it just makes it difficult. Next slide. Next question, can you comment on scalability? I'm not sure what you mean by this one. It is possible to track a lot of units with direction finding, but it will impact on the complexity on the application layer to do that. Next. How to decide between using connection and connectionless modes for a specific application or the guidelines? No, there's not really. It's a use case decision that you need to do. If you want to track a lot of units where you don't necessarily know where they are and they're going to move around and so on, then connectionless is normally the best way. If you have one unit that you want to track all the time and you want to know exactly where it is at any point in time, then using a connected mode is probably a better way, because then you know where that you have access to it continuously and so on. So it's a bit tricky one. Then it comes, which is the lowest power SSC supporting direction finding. It depends. The 52811 is probably going to be the lowest one on the transmitter side, and the key reason for that is because it's the smallest part and it's the 4 dBm radio. The 52832 does not support direction finding. It's the 52833. And the 52833, since it does have the 8 dBm capability, will use a little bit more power when you're doing running the radio than the 52811. I think the difference is around a milliamp at 0 dBm. But of course, you have the 8 dBm option.
Okay. Paul, maybe let's do 2 more questions. We are already over time,
yes.
But I think we can do maybe 2 more.
Radius lengths of coverage area. Again, I think this one has been covered earlier, but we have tested up to 10, 20 meters. We have customers done 40 meters, and we have some guys who have done much longer than that. And then is the maximum number of CTs per second. That will depend on where you're doing the calculation. On the 52833, that is actually, if you do the angle algorithms on the 52833, it's CPU limited. If it is not doing that, it will be radio limited. You can do quite a lot, but exactly how many is difficult to say. But if you run connected mode, you should be able to do 1 every 7.5 milliseconds. So then you are at what is it, 100 something. Okay.
Okay.
Yes. So we will try to see how many questions we are able to answer. So we can start with the first one. So Finn, can you get it on the screen?
I think we have a couple of questions left from this morning's webinar. Maybe we start with those.
Okay. So the first question is how you should decide between using connection mode or connectionless mode when you're doing a system. One thing to have in mind here is that when you're doing this, if the transmitter has to be seen by multiple locators, you run into a issue if you try to connect to all of them. So in those kind of cases, connectionless would probably be the preferred one. If you want to do a one-to-one between the locator and one unit, then connected mode will probably be the better option. But you will need to look into the mapping on how many units you have and how many of them will need to be connected or tracked at the same time. Then there's a question if a smartphone can be used as a tag. To our knowledge, there are no phones out in the market today that supports AoA or AoD. So they haven't enabled it. So because of that, we don't see it as being used. AoD is the most likely use case for this. Will the radiation pattern of the tag affect the accuracy of the AoD system? Not unless the signal strength becomes so weak that you can't get good enough data to run the algorithms. But of course, if you have a very loop-sided radiation pattern of the tag, then you get an issue. We use the DKs for all the testing on our side, and that's the standard strip antenna along the PCB side. Then there's a question for Bluetooth low energy earbuds reference design. Is it possible to use already existing antenna on the kit for this one? Yes, there is no special needs for the antenna on the single antenna device. You just have to have into consideration the radiation pattern and the polarization of the signal if you're going to use more devices. And then there is the final one from earlier today. Is what is the difference between the Bluetooth direction finding and Coupa? Because Coupa also have a solution here, and the difference here is that they use the same kind of physics behind the solution, but the packet, the on-air format, the packet format, and all these kind of things are different because the Coupa solution is proprietary. It's not the Bluetooth 5.1 solution. And then it is, can you use CTE for connectionless direction finding in primary advertising channels? No, this will be a clear violation of the Bluetooth specification. This is why you have to use the periodic advertising when you're doing CTE. So next. The question if you can do a reasonable AoA angle detection with only 2 antennas. This is a difficult thing to answer. We recommend to not do it. The reasoning behind that is quite simple, that if you have multipath effects, it's very likely that if you have multipath effects and it only needs to affect one of the antennas, then your system is non-functional immediately. If you have multiple antennas, then it's easier to handle that. If you go with 2 antennas and accept that, then the distance between them should be less than half a wavelength, so less than 0.5 lambda, and that has to do with the mathematics to be able to find out the angle. Do remember that when you use 2 antennas, you can't discern if it's in which direction it is, if it's in front of you and the back of you, and so on. Next. Then there is a question about the U-block solution, which is limited to 25 tags. This has to do with the amount of devices you're able to sync up with at one time. So they put in a limitation there. There could be that this is a RAM limitation as well, but I think it is because of the sync time to be able to fetch in with 25 tags. This is not something that we can control. This is something that you will need to talk to U-blocks or the integrator about. But there should be possibilities to do things on the application layer to be able to support more units. But it's outside the scope of what we will cover with our devices. So the next, yes. We have customers who have done testing for way more than 15 meters. You cannot combine Bluetooth direction finding with long range, and the reasoning behind that is that long range uses coded PHY, so it flips bits up and down all the time to be able to get the range up, and that goes against the CTE where you have the continuous tone, so it won't work. This one, if you can use the 21540 for longer range, we have not tested it, but have in mind that if you want to run things with Bluetooth in Europe, the maximum output power is 10 dBm. When you are doing, if you're using the 52833, you are at 8 dBm, and you will then only gain 2 dB if you use a front-end module. And also have in mind that if you're doing AoD, you are transmitting over multiple antennas that will impact on the emitted spectrum, so you will need to take care of that. So it may cause issues there again. Next. Then the designs files for the kit. This one you will be able to get if you contact DevZone and say that you attended a webinar. They will be able to share the files with you. Next. Yes, you can implement AoA and AoD on the 52811 and on the 5340. Have in mind that the 52811 will only support the transmit side, while the 5340 will support both the receive and the transmit. Next. The 52840 does not support IQ samples, so it cannot be used for AoA, AoD. Have in mind that the Nordic distance toolbox is completely separated from what we do with direction finding. Next. For the sample rate that we support with the 5253, the Bluetooth standard says that you should use 1 mega samples, so 1 sample every microsecond in the reference period, and then 1 sample in each of the sampling slots for the antennas. The hardware inside the 52 and the 53 does support 2 and 4 megabits as mega samples as well. So you can upsample if you want to do that. it will be not Bluetooth compliant, so you will have to go in and adapt it on the link layer, and then you also need to adapt it, of course, on the host layer to make sure that the host supports both of these. Next. What gain in accuracy you do get by using more antennas in my linear array? That one will depend on the algorithms you're going to use. It's as with a lot of these things, I will have to say it will depend. We haven't done testing on it, so it's very difficult for me to answer that. Next. So for Wi-Fi Halo, that's out of scope for what we do today. We will have much more material coming out on our Wi-Fi offering later this year and early next year. So just stay tuned and look into those webinars. Next. What is the advantage, disadvantage of BT direction finding compared to UWB? For Bluetooth, and this comes with both with direction finding as well as with NDT for distance measurement. The solution with Bluetooth only will be lower power and will be at a lower cost than using UWB. UWB will provide a much faster access, a much faster assessment of the angle as well as of the distance, and the resolution with UWB is probably slightly better as well. Next slide. If you want to do AoA AoD, then the beacon will also need to support this, and have in mind that for AoA, that's quite simple. You just need to support the CTE. So if you have a 52811 beacon, you can upgrade the code to use AoA. For AoD, you also need to have the antenna array. So that one is a bit more tricky. And on the sync process for connectionless mode, basically what happens is, if you look at the diagram in the slide, you first need to get one packet in the primary advertising channels that will point you to a packet in the data channels. You need to wait for that one. You need to pick it up, and that one will tell you where in time the period that advertising train is and which channels they are and the hopping schedule and everything. And from getting this one, from getting the primary advertising to or on the train, it will take some time, and that's part of what limits the lock-in, the sync time for periodic advertising. But you can read more about this one in the Bluetooth spec. And then there is a question for the support for core hardware antennas in the SDK. There is not. But the primary thing that you need to do if you're going to use the core hardware antenna is you will need to take the code in the sample. You will need to change the pin out for which pins are controlling the muxes, and you will need to change the pattern that you generate to control which of the antennas is being used. And besides that, most of the code is going to be unchanged. So it should be a fairly straightforward thing to do. For strategies for available to support large number of tags, this is something that will need to be done on the application layer. This is not something that's in scope for what we deliver today. The Insight Dev Kit should work with AoD in the same way as the testing we have done. As far as I know, it hasn't been verified. Yes, the question is if you can change the connection interval. Yes, you can change the interval. It's not a problem. If it doesn't change, that means that it hasn't been changed in the correct way. So you will need to go through and see how this is actually going to be set up. I have not seen any. I'm quite certain there's been quite a lot of studies done. So you will be able to see how it works. But again, it will depend on the algorithms, because in the algorithms, you can build in resilience against multi-path issues. And then the question of how many advertising beacons, as said earlier, it depends on the solution that you have available. If you try with the U-blocks, they have a limit of 25. If you change the code on the application side, you can do a lot more. Yes, you can use CTE in a connection-oriented data transmission. There are samples in the SDK where we do that. It's called, if you look at the direction finding connect central and the connection the direction finding peripheral samples, they do a connection oriented. What advantage does an increased number of patch antennas in an array provide in the design? You will get an increased accuracy of the angle, but also have in mind that it has to do with the spacing and so on. If you have a larger array, you will get better performance. And since the maximum distance between them is half a lambda, if you want to make a larger array, you need to have more antennas to do that as well. We started out with 16 because we wanted to have, or 4x4 because we wanted to have a good data set, and then we would be able to trim it down to do an L shape like u-blox is doing, to be able to test the performance of that compared to the large array as well. Yes, where you can find antenna design support, we have a space on our website for third-party partners. u-blox is getting added today or tomorrow. In there, we will add more. There will be a webinar probably in Q1 with the new partner. They were not ready to join us to do it this week because we were hoping to do it now, but there will be more coming from that side. How accurate the direction angle can be achieved, we are seeing with the antenna that we used in the sample in the presentation today. We are seeing between 6 to 10 degrees. Accuracy can be achieved. We have seen that with other designs you can get better. We have seen numbers down to 4 degrees, but it will depend. And you can see clearly that it's impacted by size. We had one partner who did an antenna which was larger, and they made a smaller one, and they went from 4 degrees of accuracy to 10 degrees of accuracy by cutting the size. So it is impacted directly by that, and it has to do with the mathematics. We do not refer to commercial deployments or customers. What would be the ideal range to be in TX and RX to get power? What's a multi-phase code? What would be the ideal range to be in TX and RX? It depends on the setup and everything. As we said, we have done measurements up to around 20 meters. We have customers done 40 meters, and we have researchers who have done measurements up to several hundred meters. It depends on the use case, what kind of accuracy you need.
Okay, 2 more questions, then we're done for today.
Yes, for distance measurement and trilateration can be used instead of using direction finding. The power consumption will be in the same range for these. The difference between direction finding and distance measurement will depend on the use case, which one will be better. You can probably get a slightly better accuracy with direction finding than you can do with the trilateration. But the trilateration, you only need single antenna devices, so it's easy that way. The hardware in our device allows you to append the CTE to any radio packet, and it can also scan for constant tone inside packets, and you can turn off the whitening. Everything is possible in this regards. But it will not be Bluetooth qualifiable then. We did this one on our own side where we wanted to do a quick fix. It was the easiest way to do it, to just append it on the primary channels. But then it is not compatible with anything else. It's a fully proprietary solution.
Okay. Yep. With that, we have actually managed to answer all of our questions. We are also close to being on time. As always, we'll make a recording of this webinar available later. We'll cut both Q&As together, so you'll be able to see all of the questions or hear all of the questions. There's also a handout already available here on the webinar if you want to have it, but we'll also update and upload the slides on here together with the webinar. And with that, thank you all very much for attending, and see you on the next one.